All right, let's get going. So welcome everybody to the 2022 UW ECE Research Showcase. I'm really glad that you're joining us. I'm the chair of the department. I'm Eric Clavens. I'm also a professor here. I've been here for about 20 years. I'm really happy you're all here, and I'm looking forward to connecting with you all in the poster sessions and in the various different activities we have for you today. I want to thank all of the industry representatives who are with us today from companies all around the Pacific Northwest, the country, and actually all over the world. I want to welcome the prospective grad students who are visiting our department virtually today. So if you see a prospective grad student, your job is to tell them how awesome the University of Washington is, UW ECE is, and how amazing Seattle is. And let's see, and hopefully we're going to have a lot of opportunities for you all to interact with each other and with some of our top grad students who will be speaking today. So this is the 6th year that UW has held this research showcase. It's the 2nd year, I guess, we've done it virtually. Hopefully next year will not be virtual. And we see it as the venue for us to highlight the outstanding work of our grad students. There's 28 projects that we'll be showing in posters, and they really represent only the tip of the iceberg of the 464 graduate students in the department. So it was a competitive process to get your poster in here, so congratulations to those of you who have your posters, and we'll be presenting them. That is awesome. Last year, our department raised about $21 million in research funding from government sponsors like the National Science Foundation, the Department of Defense, the National Institutes for Health. We also raised money from companies like Microsoft and Boeing and Google and Amazon and Intel, and from a variety of foundations and other funders. It's a very robust funding situation. And it's led to breakthroughs in papers, research papers, devices, software, patents, spin-outs, and so on. And most importantly, all this funding supports the careers of our students who go on to become professors at other universities, CEOs of startup companies, and leaders of all types. So the people that you're talking to today, tomorrow will be running companies and doing all sorts of amazing things. So get to know them. The research agenda in UW ECE spans all the core disciplines that you would find in an ECE department, including things like computing and networking, data science, photonics, nanotechnology, power and energy systems, circuits, robotics, and control systems. These are sort of the horizontals of our departments. A lot of the projects that you'll see and a lot of the work that's being done in the department is more cross-cutting, sort of the verticals of the department. These are things like quantum information science, which brings together a lot of disciplines. Same with things like brain-computer interfaces and sustainable energy technology. So look for those kinds of themes in the department of these interdisciplinary groups, not just among our faculty and students, but between our faculty and students and other departments, other institutions. It's really an amazing interdisciplinary place to be. Just as an example of that, Professor Azadeh Yazdan, is she here today? I think so. Looking for her icon, there's too many. Recently received a $3.2 million grant from the National Institutes of Health to investigate ways neurotechnology could introduce targeted changes in the brain, leading to better treatments for stroke. Co-investigators on the grant include UW professors Amy Orsborn, who's joint between ECE and bioengineering, Eberhard Fetz and Ricky Wang, who are in other departments like neurotechnology, bioengineering, physiology, and biophysics. So that's an example of where the research benefits from being at such a powerful university really take that project a level up. And you'll hear about a lot more of these interdisciplinary centers and activities on campus. Just a few of them that you might hear about that UW ECE takes a leadership role in. There's a new Amazon research hub that is led by our own Josh Smith, who's here on the call. There's Quantum X, which is a quantum information and science center. We have the Center for Neurotechnology. There's the Clean Energy Institute. the Center for Synthetic Biology, the Institute for the Foundations of Data Science, the Molecular Engineering and Sciences Institute. All of these things are efforts on campus that ECE people take a leadership role in, and that you'll see sprinkled throughout the talks today. So ask people about that and really try to get a sense of the broad spectrum of research going across the university and the region that ECE intersects. So we're going to have two best poster awards. So at the end of the evening tonight, stick around. We'll be presenting awards to the two top research projects. We have a team of judges. We won't tell you who they are, so you just have to talk to everybody as though they're a judge. I don't know. And we'll have a sort of best foundational / theory award and a best applied research award. This year's prizes include a departmental sponsored cash travel grant to be used to go to any research related travel that you want for the grad student. And we also will have an applied research award, and this is from Amazon. And actually, let's see, so this is the robot that we'll be giving away. So here it is. This is the Amazon Astro household robot. So it has a little face, it has a personality. You can have it keep track of your pets at home and log into it from far away. It can carry things to your friends around the house. And what's interesting about that, among other things, is that this robot's really intelligent. So they've actually sent us the box. It just showed up today. I don't know if you can see that. So there's the box, and it says only winners should open. And that's because the robot literally imprints on you when you open it. So there's like this whole startup procedure where you talk to it, it introduces itself, it learns about your house and who you are and probably recognizes your voice. So they've told me specifically that I cannot open this box over here. So whoever wins is to come by, take the box, bring it home, and open it up with some kind of user manual that defines a ritual that's very important. Anyway, so that's exciting, and we thank Amazon for donating that robot. Apparently, Schwartz was telling me there's not many of them around yet, so you can be the first on your block with an Astro robot. In closing, I move on to the next part of our research showcase here. I want to thank again our industry friends for your valuable partnership. I look forward to talking to you today and growing our partnerships and relationships. I want to thank the visiting grad students for considering our department. I hope you see all the awesome reasons to come to our department here today. I think you'll see many. And I'd like to thank our Associate Chair for Research, Mariam Fazal, who's there with the purple background, and our events team for organizing and facilitating and designing this event for you. And I'd like to congratulate all of the students for presenting and sharing your research with us today. If you have any questions about the showcase, the staff will be here in the main room, so you can ask them, or you can use the Zoom chat, or you can actually email events@ece.uw.edu. So our next item on the agenda is to have Professor Schwartz Patel give us a talk about his research and what's going on in his world. So Schwartz is the Washington Research Foundation Entrepreneurship Endowed Professor in Computer Science and Engineering and Electrical and Computer Engineering here at the University of Washington. His research interests are in the areas of human-computer interaction, ubiquitous computing, sensor-enabled embedded systems, and user interface software technology. His work includes developing new sensing systems, energy and water sensing, mobile health, and developing new interaction technologies. He's also a founder of Zensi, and he's a co-founder at Snoopy, and is developing a product called Wally Home. And I can tell you all sorts of things about awards and so on, but I want to let him get to his talk. It's really, really interesting. So without further ado, Schwartz, thanks for speaking with us today, and you have the floor.
Great, thank you. I'm gonna just bring my slides up, so give me a moment. All right, Eric, can you give me a thumbs up if you can see my slides and hear me okay?
I can see you and I can hear you.
Perfect, awesome, thank you. Thanks for the introduction, Eric, and welcome everyone. What I want to do is talk a little bit about some of the research that my lab is doing. And the idea here is to just give you a quick tour of the various things we're working on and dive deep in one particular project to give all of you a sense of the breadth of research that we all are doing in ECE here at the University of Washington. Often when you think about computer engineering or electrical engineering, we often have this mental model of what that might be, but I just want to hopefully break away from that traditional mental model and give you a sense of the limitless types of projects and research projects you can work on in ECE. So what I want to talk about today is some work my lab has been doing around how to leverage mobile phones for in unique ways for healthcare. But before I do that, I just want to give you a brief overview of the kinds of work, the kinds of projects my lab does. So I run the UV Comp lab, and you'll see posters from my students, the poster session. You can also visit the website. As Eric said, my lab does a lot of work in energy monitoring, healthcare. We do work in sensor systems and also new interaction techniques, things for AR, VR technology, and really looking at the intersection of machine learning and AI and sensing. So how do you supercharge existing sensors with machine learning to drive new capabilities? And that's kind of what we're passionate about. And my students span everything from circuits, hardware, machine learning, AI to human computer interaction. That just gives you a sense of all the different topics that one could work on in ECE. But one thing I want to dive into is a little bit into the work that we're doing in healthcare. If you think about healthcare in general, it's really, one way to think about healthcare is that its history is full of lots of different paradigm shifts. Everything from new therapeutics and vaccines, new imaging technologies, and also things related to surgical robotics on how you actually do surgery in a much more efficient, but also safer and non-invasive way. These are all major paradigm shifts we've seen in the last century in healthcare. One of the areas that has been a major paradigm shift in health has been point of care diagnostics. The ability to diagnose a disease or a condition at the time that you're being seen by a professional or a healthcare professional. This is a canonical example, which is basically an ultrasound machine. So you can actually, assess what's happening if you have somebody that's pregnant and you have an ultrasound reading that you can do that at that particular moment. And so this is something that is becoming more and more ubiquitous, the ability to diagnose a disease so you don't have to wait for a laboratory result to come back or something to be overread where it might take a few days or maybe a few weeks to get a result back. On top of that, we're in this interesting paradigm shift of in healthcare where things like mobile devices and devices connected to mobile phones are starting to be provide diagnostic capabilities. Here's an example of a pulse oximeter connected to a mobile phone that gives you SpO2 readings, something that now starts to enable home healthcare, telemedicine, looking at how do you move away from the four walls of the hospital and enable continuous care. And a lot of us have probably started to see a lot of this given COVID and telemedicine on its rise. And on top of this, there's this added trend where we're moving to the space of wearable computing, where you have devices that are on the wrist, shoes and socks and shirts that are able to capture biosignals in a more continuous manner, where continuous measurements could actually enable other kinds of diagnostic capabilities, where you can see trends happening, where you might be able to diagnose a condition pre-symptomatically. And so this is a new area where the intersection of computer science and electrical engineering and sensing has really enabled this field. But one thing my group's been really passionate about is looking at, well, how do we take advantage of the phone, the most ubiquitous computing platform on the planet right now, 5+ billion smartphones on the planet right now. How do you take advantage of the thing where a lot of people are already using in their daily lives to enable healthcare? We already use it for telephony, gaming, entertainment, information sharing, but how can we enable this device to help you with your healthcare journey? Often we take the phone for granted in terms of its capabilities. A modern phone has multiple cameras, one in the front and in the back. It's got multiple speakers, accelerometer, gyro. It's got a bunch of antennas, often defying physics in terms of the number of antennas you can jam into a phone. It's got a capacitive touchscreen, microphone. And often these are things that we think about just for maybe speaking to somebody on the phone, maybe just interacting with the phone or taking pictures for photography. But these things are more and more capable now. The camera that's in a modern smartphone is as good as some of the latest SLRs, or some of the camera or the CCD technology in the cameras are as good as some of the imaging technologies you might actually find in a clinical setting. And so the thing that my group has been doing is how do we use these existing sensors on mobile phones, couple them with machine learning and AI, and kind of push the boundaries on what you could do with them in healthcare. So some examples include, on the left here is an example of a tool that we built that uses the microphone to essentially create a way to be able to assess what your lung function is for people with asthma or COPD. So instead of having to use a spirometer, which is this dedicated device where you blow into it, it has a sensor in it, and it gives you an assessment of your lung function, you can actually use machine learning on top of a commodity microphone that's already on a mobile phone to do spirometry measurements for somebody that has asthma without any additional hardware at all. So think about how you could scale that. You could scale that through any phone in the world, and you can enable telemedicine use cases that just weren't possible. The example in the middle is a tool that we created called BillyCam, which is a bilirubin, a digital bilirubinometer that just uses the camera to assess how much bilirubin is in the blood of a baby without having to pull any blood out of the baby. So this is a computer vision based approach that looks at the yellowness of the skin to assess jaundice for newborn babies after they've been discharged in a non-invasive way. The example on the right is using the camera and flash on a mobile phone that assesses how much hemoglobin is in your blood, again, without pulling any blood out of your body. It uses a hemochrome analysis of the light being absorbed and reflected through your skin to basically see how much plasma versus water is in your blood to give you a hemoglobin concentration, again, non-invasively, which could be used in a home setting for either managing anemia or somebody with sickle cell anemia. So you can imagine the power of what you could do with these ubiquitous sensors and devices. But one particular area I want to talk about today is around rapid diagnostic tests. These are things you're probably pretty familiar with antigen tests that you might have to take or your kids might have to take. These are rapid diagnostic tests that are essentially at-home tests or tests that you can take very quickly and you get an immediate result. You know, pregnancy tests are an example of that. These COVID antigen tests are examples of that. Malaria tests are examples of that. These are lateral flow assays where when you take a sample and you put it on this particular cartridge, you'll see a color change or a line appear. And my lab's built some tools where you can actually make overreading these easier. You take a picture of it and a computer vision algorithm can be very precise in saying that, yes, the line is there or not, or yes, we do see if visual assessment doesn't work, right? So sometimes the line might be hard to read or whatnot, but these are visual RDTs. So these are very ubiquitous, and COVID antigen tests are a great example of that. But one example of a test that's harder to do is diabetes screening, in particular glucose screening. Glucose screening, there aren't a lot of visual RDTs for these. There are some, but they're not as accurate. And sometimes for diabetes screening, you need to be fairly precise in terms of the actual measurement in milligrams per deciliter. So a binary color change doesn't quite tell you if somebody is pre-diabetic or has diabetes because the margins are really important. In terms of diabetes screening, 10% of the world has diabetes, and that's just the only people that have reported that they have diabetes. It's known to be even higher than that. And about 30% of certain countries, their population are pre-diabetic. Just think about it, 30% of the world is probably pre-diabetic. And that's only in terms of what we have in terms of reported information. So the problem with diabetes screening is that you have to have a device kind of like in the middle, the bottom here, which is a glucometer, which you take a little sample of blood, you put it on a sample, and then you put it in a machine like this AccuCheck device here on the right that gives you a reading in milligrams per deciliter on your glucose levels. So basically your sugar levels. The challenge is that if you had to screen everybody in the world for pre-diabetes, you'd have to send a device to everybody and a test strip, or you'd have to send them to a clinic. So one of the things that my group has been working on is how do we actually do this in terms of deploying it in a larger scale where you don't need the device, you only have the strip. And so we've developed a way to do this on a phone. So the left is an example of a diabetes strip, a custom diabetes strip that we've built that can be deployed to pretty much anybody in the world. You can drop ship this in mail. It's so flat that you can put it in an envelope and use your ordinary phone to read the results. So you don't need a dedicated device to read the strip anymore. So this could be used if you wanted to massively screen for pre-diabetes in a country. The Ministry of Health in a country could actually deploy these through either community health workers or through the mail, and people can actually do a screen at home to see if they're pre-diabetic. Because then you don't have to worry about deploying the readers everywhere. So this is a custom strip that actually uses the touch screen on the phone to read the actual results. So we essentially turn the touchscreen, the capacitive touchscreen on a phone, into an ADC that actually samples this strip so that you don't need that device anymore. So you can imagine just shipping a couple of these for pre-diabetics, maybe once a year, maybe once every couple of years, maybe a couple of times a year, but you don't have to have that device. So now you only have to manufacture the strips, which you would already have to manufacture. They're a little bit, these strips are a little bit smarter than a regular strip though. It has a little bit of electronics in it to be able to enable amplinometry to be able to detect the ions that happens from this enzymatic reaction from the little sample of blood you put on the strip. It only consumes a few microwatts of power. So you need a little bit of current to get this thing going. And so the way it works is there's a little tiny photodiode that harvests just enough energy from either from the flash on the phone to give it that forward current to be able to enable amplinometry on this particular strip. But everything else are passive components. So over time, you can imagine these things being printed or actually reducing the number of components here to really drive the cost down. But the interesting thing here is that this is a disposable strip. So one time you strip, but you don't need the device itself. And so what happens is as the enzymatic reaction is happening and we sample with the sampling circuitry, the results are actually encoded as touch events. So to the phone, it actually looks like you see a bunch of a series of touch events. So we can pulse width modulate a bunch of touches to the phone, and then the app running on the phone basically can infer those sequence of touches to the amount of the glucose level or the amount of sugar. In this case, it'd be in milligrams per deciliter. And so the way it works is the whole thing is self-contained. It actually has an edge on it that's sharp, so you can it gives you a little bit of a blood sample. You put it on the strip itself, and then you just lay the strip on the phone, and you peel it back, and you put the other back part of it on the flash, and that's all it is. So there's no modification to the phone at all. So we did a clinical study. So our students actually did a clinical study recently that showed how well this works compared to an FDA-cleared, a pretty ubiquitous and off-the-shelf a glucometer called the AccuCheck device. So the AccuCheck is in pink or red, depending on what your color looks like on your end, and purple is the glucose screen. So basically the phone app using our custom strip. And as you can see, for across the board, the accuracy is pretty consistent for low diabetic, for somebody that's non-diabetic, even pre-diabetes, which is roughly about 140 to 200. So it tracks very well. The interesting thing is that the phone-based glucose screen actually outperforms an AccuCheck at the higher ends when somebody is diabetic. So this was a fascinating result for us. Part of the reason for this is because we can run the sampling algorithms on the phone, we can actually add a lot more denoising algorithms to it. The modeling algorithm, the machine learning model is actually much more complicated, something that you can run on a phone versus a small embedded device that these glucometers are, which basically are. And so the statistical analysis and the modeling techniques are a little bit more advanced for us. And so in fact, it can outperform it. So if you would apply a similar algorithm, probably in a glucometer, you could probably get similar results as well. So it's interesting, you can use the power of a mobile phone that's already kind of in your pocket or your purse or nearby to actually enhance the results of this on top of what you can actually get from just the phone sensor itself. So these results are incredibly encouraging. So at the same level of accuracy as an AccuCheck, you can do pre-diabetic screening. And so this is something that we're starting to continue to do more analysis and reporting on and doing more studies with. But this was a clinical study that we had just finished maybe a few months ago. So I just want to give everybody kind of a taste of the kind of work that we're working on, and wanted to share at least this one project with you and to give you a sense of the kind of work that our group has been doing and the kind of work that we see in ECE. And hopefully this gives you a sense of the breadth of work we do in ECE. The work we do here is impact driven. You know, we think about, in particular, my lab looks at global health, looks at health equity, looks at how do we create technology that can be deployed to anybody. Looking at novel applications, you know, Eric just showed you a robot that is pretty novel. We have colleagues that work on those kind of technologies. But the other thing that's exciting about ECE is that our students have a fundamental understanding of the entire computing stack. They can solve a machine learning problem, they can solve a signal processing problem, or they can actually go all the way down to the circuit level to create the new sensing technique that may not even exist and create that technology and go all the way up to the application. I mean, that is the most exciting, you know, type of research you can do is you can work all the way up and down the entire stack, where you can bring to bear latest algorithm technology or latest embedded or sensor technology and bring it together. The other thing that's really exciting about the work that we do in our area is that we have like-minded industry partners in our region. We have top tech companies like Google, Amazon, Microsoft, Apple in our region. They'll literally be next door to us, very close by. In fact, a lot of our colleagues go back and forth between industry and academia as well. Our students have internships and off-cycle internships. They're so close that they can intern during the academic year. And that industrial partnership is super critical as we think about scaling, looking at technology that's just so hard to get our hands onto. The example of the Amazon robot that you just saw at Astro. We got our hands on that because Amazon's right in our backyard. And so this is something that we often don't think about, is the university is a lot bigger than just the university campus itself. It's the ecosystem that we're within right now. And Seattle is one of the fastest growing technology ecosystems. And in addition to tech, we have med tech, bioengineering firms that are growing, and philanthropic organizations like the Gates Foundation and PATH, who are really passionate about taking these kinds of technologies and scaling them globally. I mean, there's not a lot of places in the country where you could have that kind of synergy around a university. So I think that's something that my students have really taken advantage of and really leveraged. Pretty much every single one of my students you probably would talk to have done internships, but not only have done internships, they have continuous collaborations with industry partners, even when they return. So I think that's something very unique about what we do in ECE as well. So with that, thank you for your attention. Hope you get to go to our website and take a look at some of the other stuff we're doing and be able to talk to some of the students that are doing cool stuff like this as well. So thanks, everyone.
All right, thank you so much, Schwartz. Amazing work as always. It's always inspiring to hear you talk. And I look forward to hearing details with your students' posters. So speaking of posters, the next thing to do is a lightning round of posters. So Emily is going to, I guess, call your name. Is that right? What are you going to do? Yeah, so she'll call your name, and are you showing the posters?
Yeah, that's right.
Okay, so, and the idea here is this is an advertisement for you to get people to come into the breakout room for your poster. This is not you describing your entire PhD thesis. That's what you're supposed to do in the breakout room, okay? So the idea is you've got like a minute. That's not a long time, okay? That's like a short Super Bowl commercial amount of time to say what your name is, what you're working on, and why people should come and hear more in your poster, okay? That's the rules. And if you start going too long, Emily is gonna just go to the next poster. Right, Emily?
Right. I have Jesse here with me to help keep track of time. So.
She's got like a timer or something like that. Okay. So that's the next plan. Emily, take it away.
Perfect. Thank you, Professor Eric Clavens. But before we get started into sharing my screen here with the student presenters and their research posters, we would like to request that everyone please hold their questions towards the end. We will specifically have an opportunity for questions after these presentations. Well, we will break out into breakout rooms and have the chance to interact and ask your questions there with students. So without further ado, we'll start with our first group. Let me share my screen here. Here we have harnessing optoelectronic noises in a photonic generative adversarial network with Chanming Wu. This group will be in breakout room number 1.
Okay, so thanks for introduction. And hello, everyone. I'm Chanming from Professor Volli's group, and our group is the photonic device group. And the topic today is the harness optical noise in the photonic GAN network. So optics recently become a potential platform for neural network applications since it allows the data to be transferred in parallel at the speed of light. So here we build a in-memory photonic tensor core using the optical phase change material to perform the linear matrix and matrix multiplication in each layer of the neural network optically with the electronic interconnections to perform the nonlinear function. However, since due to the analog nature of the photonic network, so it's much noisier than the digital computer. So error will accumulate between layers and degrade the performance of the network. So here we try to utilize the noise in the real hardware. So here we take the GAN network as an example, which is trained to generate new patterns. So here we harness the noise in 3 different ways. First, we use the optical random number generator to generate the input to the network. Second, we also perform the noise-aware training algorithm that maps the trained parameter to our devices. Third, the noises will naturally be involved during the real-time operation. So here we show that our method could efficiently increase the quality and diversity of the generated patterns, even compared to the ideal noiseless hardware. Yeah, so that's all of my project. So if you are interested in my research, you can find me in the breakout room number 1. Yeah, so that's it. Thank you.
Perfect, thank you. Up next, we have electronic mode stirring for improved backscatter communication group with Sarah Reyes and James Rosenthal. This group will be in breakout room number 2.
Hi, my name is Sarah Reyes. I'm a 4th year undergraduate researcher at the Sensing Communications and Computational group here at UW. And basically our project is about ultra low backscatter communication that has the ability to enable multi-day neural recording sessions for neuroscience experiments in non-human primate models. However, most neural recording in primates is conducted in metal animal cages, and that adversely affects the communication system and affects the signal integrity that you get. It creates this dense multi-path effect that in turn affects the signal integrity. So we use a method called electronic mode stirring to basically reverse that. And we attach these electronic mode stirring antennas to the top of the cage to improve the insertion loss shown throughout the cage. And these heat maps kind of indicate that darker spots have worse insertion loss and lighter are better. And you can see that with electronic mode stirring, there's a significant improvement in the signal integrity that you get. And that's kind of what I'm going to be presenting about. So feel free to join me in breakout room number 2. Thanks.
Perfect, thank you. Up next, we have the Mixer first 4-element group research group with Dennis D. And this group will be in breakout room number 3.
Hi, I'm Dennis Dostolo, 3rd-year PhD student in the FAST lab. So an increasing number of 5G devices are utilizing the millimeter wave spectrum to realize massive connectivity and high data rates. To compensate for the higher path loss, these transceivers are implemented as phased array beamformers, achieving array gain and directional steerable beams. Conventional beamforming is done by implementing phase shifting in the analog domain, which can degrade front-end performance, increase power and area, and in general only accommodate a single beam. So our proposal is to create a beamforming system that is adaptable and can steer multiple concurrent beams by applying the phase shifting in the digital domain. So we present a 4-element V-band digital beamforming receiver. To reduce the power and area across wide signal bandwidth for each element, we implemented a mixer first front end and an ADC with adjustable resolution. Our chip was fabricated in TSMC 28 nanometer CMOS is shown on the bottom right. And so I will go into greater detail about the architecture and measurement results in breakout room 3. Thank you.
Great, thank you. Up next, we have broadband long-delayed self-interference cancellation for use in full duplex transceivers with the group Zishan Lee's group, and they'll be in breakout room number 4.
Hello, everyone. I am Shichen Li from FAST Lab, Professor Rudel's group. We mainly worked on a project to explore a new opportunity to enhance the higher wireless data rate for next generation communication. Unlike the conventional frequency division duplex system, the full duplex system can combine the transmitting and the receiving signal into one frequency to increase the spectral efficiency. However, that requires a large suppression on interference signal in order to be used in commercial radios. In this project, we designed a full duplex transceiver with multiple cancellation paths on chip in TSMC 40 nanometer CMOS technology. And also we combine it with the Altera FPGA board to demonstrate both short delayed and long delayed self-interference cancellation across very broadband bandwidth, mainly for Wi-Fi applications. If you are interested in this project, please drop by room 4 and I can show you more details about this research at that point. Thank you.
Perfect, thank you. Up next, we have the Luna research with Jiarui Kai's group, and they'll be in breakout room number 5.
Okay, thank you for the introduction. Hi, everyone. My name is Jiarui. I'm a PhD student under Professor Jenna Huang's group. working on computer vision topics. I will present our recent work on open cell recognition. Basically, we answer two questions in this research. Number one is how to train an unbiased model with extremely imbalanced data set. And number two is how to handle those novel and out of distribution data in testing. Thank you for the opportunity. I will meet you in breakout room number 5 if you are interested.
Great, thank you. Up next, we have demonstration of an optimized large-scale optogenetic cortical interface for non-human primates with Devin Griggs' group, which will be in breakout room number 6.
Hi, I'm Devin Griggs. Optogenetics is a powerful neuroscientific tool which allows neurons to be modulated by optical stimulation. Despite widespread optogenetic experimentation in small animal models, optogenetics in non-human primates remains a niche field, particularly at the large scales necessary for medically translational multi-regional neural research. We previously published a large-scale chronic optogenetic cortical interface for NHPs, which was successful but came with a number of limitations. This work improves upon the stability and scale of our previous interface while using more easily replicable methods to increase our system's availability to the scientific community. Specifically, we demonstrate the long-term optical access to the brain achievable using a commercially available transparent artificial dura with embedded electrodes, showcase large-scale optogenetic expression achievable with simplified surgical techniques, and effectively modulate the expressing areas at large scales on the order of 1 square centimeter, which produces behavioral effect. I'm Devin Griggs. Please meet me in breakout room number 6. Thank you so much.
Great, thank you. Up next, we have policy gradient descent for control with Yu Sun's group, and they'll be in breakout room number 7.
Hello, everyone. This is Yue. So my topic is about feedback controller design. It has a long history in the control theory, and recently it is revisited in reinforcement learning. But actually, there is a difference in methodologies in these two domains. In control theory, people use convex parameterizations, while in like today's reinforcement learning, people do non-convex optimization in policy space. We build a connection between the two spaces and show the success of non-convex method by this kind of bridge. And we show the generality by showing that this property holds for a family of control problems. So I'm Yue, and I'm in breakout room 7. Thank you.
Perfect, thank you. Up next, we have a game theoretic model for co-adaptive BMI with Manishika Maduri, and she will be in breakout room number 8.
Hi, everyone. My name is Manishika, and I'm a third-year ECE PhD student being co-advised by Sam Burden and Amy Orsborn, both professors in the ECE department. Being co-advised is actually pretty common in the ECE department. It allows students to integrate different research areas. And in my case, my research and my project lie at the intersection of control theory, game theory, and neuroengineering. My research draws upon some of the more theoretical techniques from the Burden lab, particularly game theory, and applying that to brain-machine interfaces to explore how different machine algorithms or decoder algorithms can potentially shape user learning. My poster will focus on a game theoretic model of co-adaptive brain-machine interfaces that I developed with my advisors. We treat the brain and the machine as two individual agents that are learning together in this interface to explore convergence and stability as the brain and the decoder co-adapt. If you're interested in learning more, I'll be in breakout room 8.
Perfect, thank you. Up next, we have Diso for blockchain with Milad Fatoki, and he will be in breakout room number 9.
Hello, everybody. My name is Milad. I'm a second-year PhD student at the ECE department working with Dr. Abshahi. So talking about my project, this project, we are addressing some specific problems that we will face in disaster recovery. So we are proposing a solution for the problem disaster management, where some medical records might be considered as a secret unless there is a disaster. So in that case, they should be revealed into some appropriate authorities so the medicine can actually be available on time. So we are introducing and simulating consensus-based secret sharing protocol, this project, on the smart contracts with the goal of depositing the secret on the blockchain and having the blockchain actually to keep the secret. Shadow secret sharing has been used to obscure the secret and reveal it when the majority of the parties actually are available and they will vote for the secret to be released. So we have implemented our protocol. It has been fully functionality, has been developed in ROS code, which is like 7,500 line of ROS code. Yeah, and we have tested our primary results to demonstrate like up to that our protocol actually can support up to 10,000 transactions per second in terms of throughput. And we were able actually to reduce the gas cost of Ethereum for 6,000 times. In case that you're interested for more details, I will be in breakout room number 9, I think.
Yes, that's right. Breakout room number 9. Great, thank you. Next up, we have non-volatile programmable silicon photonics based on phase change materials with Zuron Bing's group, and they'll be in breakout room number 10.
Hello, everyone. I'm Zhuang Fang. I'm a first-year PhD student in Professor Arkamajana's group at ECE. So the background of my research is really that the current silicon photonic integrated circuits are based on the thermal optic phase shifters to tune the circuits. And these thermal optic phase shifters are very power hungry, volatile, and they are very large in the size. And most importantly, there's like a lot of thermal crosstalks between the phase shifters. In our lab, we are interested in using phase change material to achieve this tuning. The phase change material has benefits that the phase change is non-volatile and it gives a very large contrast in refractive index. So we can envision that by connecting these directional couplers based on phase change material, we can form a large switching fabric, which is non-volatile. And there's no need for a constant power supply to maintain the states. And most importantly, such switching fabric is very compact. And this large switching fabric can be used to achieve a lot of applications, such as optical signal routing, optical neural networks, and quantum information processing. So if you're interested in silicon photonic integrated circuits, please join me at the breakout room number 10 for more information. Thank you.
Great, thank you. Up next, we have tissue characterization with Smart Grasper Robot with Jana's group, and they'll be in breakout room number 11.
Hello, everyone. I'm Yana Sosnovskaya, and I'm presenting my work, Tissue Characterization with Smart Grasper Robot. The idea is to place a sensor set on the motorized surgical grasper that we named Smart Grasper Robot. And this sensor set includes ultrasound sensor, thermistor, bioimpedance sensor, and also indirect force sensing, as well as encoder that can help to get the distance between different jaws of the Smart Grasper Robot. This project involves not only hardware development for the sensor set, but also signal processing and signal analyzing algorithm development, including deep learning algorithms for learning features from different sensor modalities and fusing the data. Please join in breakout room 11 to learn more about this project. Thank you.
Great, thank you. Up next, we have non-contact physiological sensing with radar and camera with Girish's group, and they'll be in breakout room number 12.
Hi, I'm Girish. I'm a second-year PhD student in the UBComp lab with Professor Shredik Patel. And yeah, I'm talking about non-contact physiological sensing. So a lot of prior work has shown the ability to measure these radar, these heart and respiration signals, both with modalities like millimeter wave radar and with camera, except these modalities have different drop-offs. Camera underperforms significantly with poor lighting and on darker skin tones, while radar drops off significantly at distance. So this work hopes to balance these trade-offs and build a more robust, more equitable network through sensor fusion, fusing these two input modalities. And I can be found in breakout room number 12.
Yep, that's correct. Breakout room number 12. Perfect, thank you. Up next, we have millimeter scale focal length tuning in MEMS integrated meta optics with Zhe Yi's group, and they'll be in breakout room number 13.
Thank you. Hi, I'm Zhe Yi from Professor Carl Behringer's group. Our project aims to build a compact lens with a tunable focus, combining the technologies of meta optics and the micro electromechanical systems, which we call MEMS. Our focal tuning approach is based on the Albers lens, which consists of a pair with complementary surface profiles. A lateral shift between optics modulates optical power. To minimize the device volume, we use silicon nitride nanopost arrays to map the 3D conventional optics to a pair of 2D meta optics. To introduce the lateral shift for optical tuning, we use electrostatic transducers to produce precise and reproducible tuning performance, which is crucial for controllability and reliability. Our device has generated a focal tuning range of 3 millimeters with only 15 micrometers of displacement, producing a 200 times scaling between the actuation input and output. If you'd like to know more, I will be in break room 13. Thank you.
Great, thank you. Up next, we have Decentralized Safe Reinforcement Learning for Voltage Control with Wenqi's group, and they'll be in breakout room number 14.
Hi, I'm Wenqi, a third-year PhD student from the group of Professor Basen Zhang working on power and energy systems. This poster will focus on fast time-scale voltage control by inverter-based resources. The power electronic interfaces allow these resources to realize almost arbitrary controller, but designing these decentralized controllers is non-trivial. Reinforcement learning approaches provide the possibility to search for policy parameterized by neural networks. However, it is difficult to enforce that the learned controllers are safe, in the sense that they may introduce instabilities into the system. To overcome these challenges, this work we proposed a safe learning approach for voltage control. We prove that the system is guaranteed to be exponentially stable if each controller satisfies certain Lipschitz constraints. We then explicitly engineer the structure of the neural networks such that they satisfy the Lipschitz constraint by design. A decentralized RF framework is constructed to train the local controllers at each pass in a model-free setting. Welcome to the breakout room 14 to discuss more of the details. Thank you.
Perfect, thank you. And then our next group is unfortunately unable to make it tonight, so we'll go ahead and skip over really quick. But I'll go ahead and introduce the next group, the cost of an arm and a leg, designing lens for multiple dynamic behaviors with Joseph's group, and you can find them in breakout room number 16.
Hello, everyone. My name is Joseph Sullivan. I'm a PhD student advised by Sam Burden in ECE, and this is my project. So many of you are no doubt familiar with robots from Boston Dynamics, such as Atlas and Spot. And people for a long time now have envisioned these robots being employed to do work in the real world with new applications, such as robots supplementing manpower in disaster response scenarios, or in construction applications, and even in last mile logistics, such as the Digit robot. However, for a long time, the research in this area has been focused on locomotion, with manipulation behaviors being treated post hoc or sometimes as an afterthought. Whereas in all of these future envisioned applications, both autonomous locomotion and manipulation, the ability for robots to do physical work, are essential. And so we're putting forward a research program where we're seeking generalizable methods that we can use to design robots for multiple behaviors, not just locomotion, but manipulation behaviors as well. And so in the poster, I'm talking about a case study project wherein we take a limb from a quadrupedal robot and we redesign it so it can be used both in a locomotion behavior and in a manipulation task. And so if you'd like to hear more about this project and the methods we use to formulate this as a optimal design problem, please come to breakout room 16.
Perfect, thank you. Up next, we have learning and stochastic monotone games with decision-dependent data with Ariane's group, and you can find them in breakout room number 17.
Hi, everyone. My name is Adhian Narang, and I have Evan Faulkner with me, and we're both second-year PhD students advised by Mariam Fazel and Lillian Ratliff. And the work we're talking about today lies at the intersection of statistics, machine learning, mathematical optimization, and game theory. And a big assumption that statistical learning theory makes is that there is a fixed probabilistic data distribution that both the training data and the test data are drawn from. But oftentimes this assumption doesn't hold in practice. And the data that you see at test time can be influenced both by decisions that you've made in the past and decisions that other agents have made in the past. So for example, in the flowchart we have over here, if say UC Berkeley decides that SAT scores are not important for university admissions at Berkeley at all, that would possibly influence the data of admissions that are received by UW also. So in these types of modern statistical learning settings, we provide new novel algorithms that can provably converge and learn good models in these settings. So we hope you join us in breakout room number 17 to learn more about this.
Thank you. Up next, we have tunable and deterministic single photon emitters in bilayer YSE2 with quantum phonon states with Adina's group, and they'll be in breakout room number 18.
Hi, everyone. So my research is in Professor Moli's group, and we're interested in integrating systems with photonic devices. So single photon emitters are really highly desired for quantum information processing, but they can be quite difficult to integrate with photonics. So here we explore single photon emitters in 2D materials, which can be much more easily integrated with photonics. One of the major problems with emitters in 2D materials is that they have spectral inhomogeneity. So it can be quite difficult to get two emitters at the same energy. But here we use the out of plane electric dipole of the bilayer WSE2 to tune our emitters energy through like 10 nanometers range. So here's an example of two emitters on two separate devices. We tune to the same energy and wavelength. So we also observe these intralayer excitons. And in addition to these single photon emissions, we also observe a single, we observe phonon quantum states that are coupled to them, which is quite interesting. So to learn more, I'll be in breakout room 18.
Great, thank you. Up next, we have frequency resolved angular modulation beam steering with Bing Zhao's group, and they'll be in breakout room number 19.
Hello, everyone. I'm Bing Zhao Li from Professor Moli's group. My work is about to build an integrated solid-state LiDAR with our frequency-resolved angular modulation beam steering technology. So why this technology? Because there are lots of applications, such as a self-driving car, needs many robust, high-performance, compact, yet cheap LiDARs, but there's nothing available in the market. However, our technology is a good candidate. By harnessing the surface acoustic wave on the lithium niobate wafer, we can emit the light out directly from our small chip and steer it to whatever direction we want. All the angular information is encoded in the light frequency due to the AO interaction nature. Moreover, there is no mechanical moving part in this device, making it super robust. So if you want to know more about this project, please come to my breakout room number 19. Thanks for watching.
Perfect, thank you. Up next, we have Integratedcousteau optics device with solid state qubits with Itong Chen. And you can find them at breakout room number 20.
Hello, my name is Itong Chen and advised by Professor Moli. So in this project, we propose a novel way to integrate a solid state qubit, and in this case, a defect in diamonds. And we try to address the problem of the frequency inhomogeneity of the diamond qubits and using a acousto-optic frequency shifter. So if you'd like to know more about this project, please come to breakout room 20.
Perfect, thank you. Up next, we have secure frequency encryption FMCW LiDAR systems with Liban's group, and you can find them in breakout room number 21.
All right. All right, good evening, everybody. My name is Liban Hussein. I'll be presenting with Marzia today. We are both in the Emit lab, and we're first-year PhD students working with Professor Sajjad Mohsen. So robust and secure sensing and imaging capabilities are vital in future autonomous vehicles and robotics, both for accurate control and accident prevention. Light detection and ranging, that's also known as LiDAR, is a major 3D imaging technology used to do so. So I want everybody to imagine that you're in an autonomous vehicle, and then suddenly, because of a security breach in your vehicle's LiDAR system, you lose control. We can see that security vulnerabilities, including hacking of these LiDAR systems, these impose critical threats to both human safety and security. So in this work, we present a study of the different security vulnerabilities found in today's LiDAR systems. We do this through electrical optical co-simulation using MATLAB Simulink. We focus on beam steering and frequency modulated continuous wave LiDAR systems, as these have been considered to be the most secure LiDAR systems proposed thus far. We also propose a frequency encryption technique to eliminate the possibility of spoofing such LiDAR systems. We plan to implement this method by combining an FMCW LiDAR with a physically unclonable function block on a single chip. And these can be key elements for next generation secure LiDAR systems. So you can find Marzia and I in breakout room number 21, and Astrobot is on the line, so please join us.
Great, thank you. Up next, we have Open Lab Clusters, semi-automatic key points-based animal behavior clustering and classification with Jing Yuan's group, and you can find them in breakout room number 22.
Yeah. Hello, everyone. I'm Jing Yuan Li from Professor Eli Schliezerman's lab. We are interested in identifying animal behavior. So behavior experiments are performed on a regular basis in neuroscience field. However, not many studies work on the semantics of motion sequence, which are supervised by higher level intelligence. Also, earlier works require a large set of annotated samples. In this project, we work on the animal behavior identification with semi-supervised method with a few annotated samples. The system includes two parts, the behavior clustering parts and the behavior identification parts. We show that our system can boost recognition performance with only a small percentage of annotations on various animal behavior data sets and achieve comparable performance as the circumstances when the full annotations are accessible. We also turn our system into an interactive annotation tool to guide the labeling effort in the wild videos of various objects and actions for robust recognition. If you are interested in the project, please join us in the breakout room 22. Thank you.
Great, thank you. Up next, we have How Does It Sound? Generation of rhythmic soundtrack for human movements with Kunsu's group, and then you can find them in breakout room number 23.
Hi, everyone. My name is Xiulong Liu. I'm from Professor Eli Schliezerman's group. And in this work, we propose a novel system called Rhythmic Net, which takes an input video with human movements and generates a soundtrack for it. Rhythmic works directly with human movements by extracting skeleton key points and implementing a sequence of models, translating them into rhythmic sound. Rhythmic Net follows natural process of music improvisation, which includes the prescription of streams of a beat, rhythm, and the melody. And we evaluate Rhythmic Net on a large scale video data set that include body movements with inherent sound association, such as dance, as well as in the wild internet videos. And we show that the method can generate plausible music that align with the different types of human motions. If you are interested in, we are in the breakout room 23. Yeah.
Great, thank you. Up next, we have Programmable Black Phosphorus Image Sensor for Broadband Optoelectronic Edge Computing with Seo Keom's group.
Seokyeong, yes.
Perfect.
Thank you.
And yeah.
Hi, my name is Seokyeong Lee from Professor Molly's group. And the motivation of the research is a human vision system processes image and videos in very efficient manner in terms of the low energy consumption and low latency by putting their memory and processors in the vicinity. So inspired by the biological vision, our optoelectronic processor emulates the two core functionality of the human vision, capturing optical images and translating into electrical domain, like eye and optical nerves doing. And also subsequently, we recognize the data via analog in-memory computing. And then we realize this functionality using optically sensitive two-dimensional material, so-called black phosphorus, by making a phototransistor with charge trapping ability. And this charge trapping ability will give you the programmability of the device. And making this out of, in the form of the array, we demonstrate the edge detection using optoelectronic in-sensor technology and simple CNN network to recognize handwritten digits. So if you are interested more about this, you can find it breakout room number 24. Thank you.
Great, thank you. Up next, we have OPH, optical pH monitor to measure dental biofilm acidity and assist in enamel health monitoring with Manuja's group, and you can find them in breakout room number 25.
Hi, everyone. I am Manuja Sharma from UBComp Lab, co-advised by Shwartz Patel and Eric Seibel. I am presenting today about design and clinical results of an optics-based pH measuring device to assist in our oral health. Bacteria in the oral biofilm, as you can see on the left side of the slide, reacts with sugar in our food producing acid. This acid, if left unchecked, results in cavity. Previous studies have shown that tracking this acid level before and after a sugar rinse can actually help us provide site-specific information about dental health, that is even before a cavity is formed. So there is an answer to all the drilling and filling that we receive at dentist office. So for that, we need a device to measure pH without disturbing the biofilm, as well as measure pH inside of the biofilm rather than on the surface. So we have designed a fluorescence-based optical pH detector that uses low-power LEDs, photodiodes, and fiber optics to function in the range of 4 to 7.5, as shown in the middle of the slide. The device was tested in clinic on 30 pediatric subjects with cavitated and healthy surfaces. As a next step, we have also modified the spot-based device to an imaging device and performed a case study as shown in the bottom right. To know more about the working results about the device, please hop in room number 25. Thank you.
Thank you. Up next, we have analyzing neural flow using signal processing on graphs with Felix, and you'll find them at breakout room number 26.
Hello, my name is Felix Schwock, and I'm a first-year PhD student co-advised by Professor Les Atlas and Shima Abadi. And so for a long time, researchers have been fascinated by how our brain works and how different regions in the brain communicate with each other. And understanding and especially modeling those neural communication and flow processes is very important, specifically for developing better treatments for various neurological diseases such as Parkinson or stroke. And so in our group, we propose a new modeling framework to describe the neural information flow in the brain. And in this framework, the neural flow is modeled through a graph diffusion process and results in a signal that is defined on the edges of the graph and describes the flow between different regions. And compared to other approaches, we can model the neural flow on a much finer temporal scale. And if you want to learn more about how we model and analyze the neural flow, please come to my poster in room number 26.
Perfect. Thank you so much. Up next, we have broadband imaging with metasurfaces with Luan Cheng's group, and you can find them breakout room number 27.
Hey, good evening, everybody. My name is Luo Cheng Huang from Professor Arka Majumdar's group, and I'll briefly talk about broadband imaging using meta-optics. It's very exciting that camera sensors are getting smaller every day, and it's equally important for the optics to get smaller, so that your $1,100 iPhone 13 Pro Max can actually sit flat on your table, not having its camera sticking out. Anyway, we were able to make ultra-thin optical elements with thickness 100 times thinner than a human hair. We've demonstrated excellent imaging capabilities in the visible as well as long wavelength infrared, also known as thermal imaging. In breakout room 27, we will talk about how to make these meta-optics using techniques such as deep neural networks, computational imaging, extended depth of focus, and inverse design. So yeah.
Perfect. Thank you. We're approaching our last presentation here. Should storage-centric tariffs be extended to commercial flexible demand? And this is with Lane Smith's group, and you can find them in breakout room number 28.
Great. Thanks, Emily. I'm a PhD student working with Daniel Kirshen. Our research we'll be talking about today is motivated by the fact that large projected increases in demand electrification, so that's electric vehicles, heat pumps that are coming onto power systems these days, are poised to introduce many new power system challenges. So namely, we'll see increased demand peaks and new seasonal peaks. However, these new technologies can really provide useful operational flexibility to grid operators. The big question with this becomes, how can we procure this flexibility? How can we use it? And so one option that we explore in our work is using electric tariffs that are currently being put out there by utilities in order to encourage battery deployment by large consumers. And so in our work, we simulate this operation, and we find that utilities are able to benefit by consumers having lower net demand and net demand ramp rates during peak hours, which are times of high strain on the grid. But we do find that only the most flexible consumers are able to benefit. And so this motivates future work where we want to look at designing new mechanisms and new rates that are able to be more accessible to many different participants. So if you're interested in talking to us a little bit more, please stop by room 28. Thanks.
Great, thank you. So we've reached the end of our presentations here. So can we get like a really quick virtual round of applause for all of our student presenters for presenting, and all of the students, faculty advisors, postdocs, and sponsoring agencies involved in their research presented tonight. I see a little claps here and there, but we'll now transition into our breakout rooms. Each room will be labeled with a shortened name of their research title. You can also find their correlating breakout room number on student posters numbered on our event page, which I'll drop a link in just a moment here. Let's see here. Ooh, here we go. And then myself, along with Jesse Navarro, will be sitting here in the main Zoom meeting space to help direct you all if you have any issues finding a room or if you have any general questions. But in a moment, we'll open up the breakout rooms and to our student presenters, falling into your assigned breakout rooms. And then let's see here. I'll go ahead and open them.
Before we do that, Emily, just real fast, I want to please go and visit several different posters. If you see a poster session that doesn't have anyone in the breakout room, that's a good one to go to. If you see one that has 20 people in it, that's probably one you want to put off till later. So try to give lots of students the chance to explain their research. That would be wonderful. And I'll also be staying in the main session if you want to chat with me, and there may be some other faculty hanging around in this session as well.
Great. I believe the breakout rooms are open, so you're more than welcome to join them.
Thank you.
Absolutely.
All right, it looks like everybody's back from the breakout rooms. Is that right?
Yep.
So now we are going to present awards, and Mariam Fazal is going to do that. So Mariam, is she here? Oh, wait.
Yes.
Oh, you are here, good. She was deliberating and I was vamping. So now she's back and ready to go.
Yes, so first of all, thank you everyone for participating, all the poster presenters. I would like to congratulate every one of you for doing such a great job, both with the 1-minute pitch talks and the poster presentations. So all of you, thank you so much. Now we have winners in 2 categories to be announced. The first category is Best Applied Research. And in that category, our winner is, the winning poster is Broadband Imaging with Meta Surfaces. The winner is Lucheng Huang. Is he here?
Yes, I'm here.
Congratulations. Congratulations.
Thank you guys. Thank you so much.
And yeah, you will be winning the Amazon Astro robot from
Yes.
126, right over there. So
Thank you.
big congratulations.
What an honor. Thank you guys so much.
Yeah, so and the next one, so in another category for best foundations theory research, which includes things like modeling and theoretical and mathematical analysis, algorithms, aspects of engineering systems. Our winner is, the winning poster is game theoretic models for co-adaptive BMI. Manishika Maduri, is she here?
Hi, yeah, I am.
Congratulations.
Thank you.
And the award is a travel grant from ECE for research-related travel for $1,500.
Wow, thank you so much.
Congratulations to both of our winners. We are really also thankful to our sponsor, Amazon Lab 126, for donating the robot, and of course to ECE department for the travel funds. Now that our travels are restarting again, it's a good time to use these. For the winners, the ECE department will contact you to tell you how to receive your award. And again, congratulations. I'd like to also thank the judging panel who did a great job with picking the winning posters. And again, thanks to all the students. I'll turn it back to Eric.
Okay, and that pretty much wraps up our research showcase. So I would like everybody to give one more round of applause to all of our presenters, and poster presenters and speakers, and everyone who collaborated with them on these posters. Absolutely fantastic work. I'm incredibly proud to be a part of this department and to just see the incredible breadth of creativity and ingenuity and technical prowess that was presented here today. And I think that everybody should have won a prize. And if we only had 28, that's what we would have done. I'd like to thank our industry partners for coming and visiting with us today. So thank you so much. And we will hopefully be seeing you soon in more events in the future. I hope that there are still some of our prospective students in the audience, and thank you for sticking it out through the whole day. I know we started early this morning and we're still going, but we just have a lot to tell you, and it's an exciting place to be. And with that, and definitely thank you to all the organizers. Even though it's a Zoom event, it still takes quite a bit of effort to put this together and make sure that it runs smoothly. This was, I think, the most breakout rooms I've ever seen in a Zoom call before, and it totally worked and it seemed to go quite flawlessly. So thank you all for organizing this and putting it together. And thank you, Mariam, for coming up with an inspiring schedule that got everybody so much chance to interact and talk with each other. And with that, I am going to close our research showcase. Congratulations again to Manashika and Huang. And yeah, if there are any questions about UW ECE, please feel free to email me. I'll hang out a little bit here as we close. And yeah, have a wonderful evening.